Yeah, my name is Richard Russell. I'm the current vice president of the Society of Amateur Radio Astronomers and also the science lead for the Deep Space Exploration Society. So we're going to look at the Pioneer and Voyager pulsar map that was installed on those spacecraft. We're going to identify the pulsars in the map, and then we're going to see if we can triangulate our sun's position in the galaxies in these pulsars. Then I'm going to make a hypothetical trip from a known exoplanet to our sun, attempting to use the Pioneer map as a guide. Pioneer 10, as you can see on the left, they had the map was installed. W.R. Johnson, 2007, put out a paper trying to go through this pulsar map, and that gave me a lot of inspiration and steps. I'm going to follow a lot of his steps, but I went farther in using the data to actually navigate and put it in galactic coordinates. So the first step is we're going to define the hydrogen symbol. It's common, and that'll give us a common timing reference. Then we're going to determine the binary representation each line on the map. We're going to convert the binary to base 10 and then apply these to the hydrogen reference time to get the pulsar periods. From the pulsar periods, we should be able to identify the pulsars that are on the plot. Okay, so we have to find, the assumption here is that the pulsar periods are unique, and then an ETI would be able to take those pulsar periods and come up with the known pulsars, and they would know where they are in the galaxy, and therefore they could triangulate on us. I'm going to convert all these to galactic centric. That's fundamentally is assuming that the Sagittarius A star is the center, our black hole in the center of our Milky Way is the center, and the sun is actually 8,500 parsecs away from that center, and on the galactic plane. And then we're going to find, we're going to see if we can derive using the lengths and the angles to triangulate the sun's position. Once we know the pulsars, can we actually triangulate back into the sun, and how accurate is that going to be? Okay, hyperfine transition of hydrogen is when the electron is spinning in a certain direction and it flips. Okay, once it flips, it releases a photon at 1420.405 megahertz. A lot more digits there, which we needed. And so this diagram here is supposed to represent the hydrogen flip, and a physicist, an ETI physicist, might be able to identify that as a hydrogen flip, and then look up that frequency. Now that frequency would be a different time. They would have a different number for the time. Assumption here is that the center here is the sun's location. There are angles. Actually, in the galactic center is identified in this long line down here, and that'd be the galactic center. That's important because that line is a relative distance length compared to these other lines. And the pulsar angle here, and then there's these pulsar lines. Now, these pulsar lines, the lengths of these lines are not, the full length is not the distance number. The distance is actually this first part of the line down here. And there's another part of this line that is the actual distance from in the Z direction in the galaxy. Okay, so what does a pulsar line look like? If you start from the bottom where the sun is, you see there's a length from the Earth and the XY plane, and so that's along the disk length. And then you have the distance above the galactic plane, the z-axis, is a little distance, that little distance here. The rest of this is a binary count. So the assumption is they know binary, and then there's a least significant bit and most significant bit here, and you count the, you basically can count the numbers. If you do count those numbers, and I put an arrow in the direction that gave us these numbers here, you come up with these binary numbers. On each one of these, there's 14 distinct lines, and if you count them in that direction, you get the numbers shown, and that's key because that's now the binary count. Now, how do I turn this into base 10? I don't have to use base 10, but base 10 is what I decided to use based on my hint of the figure, and that comes up with these numbers here from the different pulsar numbers. Come up with these base 10, and think of it as transitions or counts. And now, how do I adjust for period? I take the 1420, 1 over the 1420 megahertz, and I divide that by the count, and I come up with a period number in seconds. Their website, but you have to basically do a search and say, okay, what are the different pulsars? What are their known pulsar periods? And then compare them with what you've got. And from that, once you've determined which pulsars there are, you can come up with their right ascension declination, their distant, their approximate distance using the database from the sun, their longitude and their latitude and galactic coordinates. And another important thing would be the P dot is this is basically the decay, the spin down rate of the pulsar, and that's important later on. Okay, once you have that, when you identify a pulsar, the pulsar database is the pulsar period that we observe on Earth. If we're 10 light years away from the pulsar, we're seeing the pulsar period as it was 10 years ago. But in reality, it's spinning down based on the P dot, and the actual base period of the pulsar at the physical pulsar is slower than what we're observing it. So it was important because depending on where you are in the galaxy, you're going to see a different period for the same pulsar because you're going to be seeing it in a different time distance from the pulsar. So it was important to come up with what is the base period at the pulsar so that you can adjust depending on where you're traveling in the galaxy. You can adjust for what you expect to see that pulsar's period from your position. And so these are the pulsar periods, the base pulsar periods based on the distance of that pulsar from the sun. The next step was to shift the galactic coordinates. If you plot those, and if you look over here, I've numbered the pulsars here. If you plot those, you will see the galactic center here, and you'll see, and then you take the distances. You'll see how that's all set up, how these look in reality in the XY plane of the galactic center. So these lines give you a sort of a false representation because they're actually your binary lines. If you actually look at what they're really telling you is that these are the distances from the sun, which is right about here, to the galactic center. The next step was to actually measure the angles. The next question was to how do I scale the distances? I had to come up with an average scale for this. What did I find out? That the pulsar map distances are they're not consistently accurate. They're plus or minus a couple 100%. There's some smaller variations, so they're not based on the actual chart. There's a lot of distance variation in those. So, but I took the the numbers that I had, and I plotted them out. But first I did the variation for the angles. The angles were a lot better. They had a lot less deviation on the angles. So if you look at this, you'll see this is the actual angle measurements. You can see that I did get pretty good. These are basically lines going through from the pulsars to through the angles. I did get a pretty good plot there. So an ETI probably couldn't find the position in the galaxy using just the distances on that chart, but they would have a lot more accuracy with the angles and triangulating with angles. Okay, so it appears that we can they can, using the angle measurements and the distances and determining the numbers, an ETI can find where the sun is. The next step was, can I actually navigate with using this and using those same pulsars? So I chose a star, Kepler 452b, which has a known exoplanet on it, and I decided, okay, let's just try that. It's 1,402 light years away, so we're going to go and attempt that. So I plotted all those. One of the first steps was I had to go determine which pulsars, where the pulsars are being seen from that, from Kepler 452b. And you can see here's the galactic center coordinates for everybody. I added the Kepler 452b galactic center coordinates on the end of this. Using the base periods, I determined what is the period of each pulsar that Kepler 452b would see at its location. I haven't done the in-between, but from its location, these are the periods that these pulsars would be seeing at that location. Then if you plot that, you can see the course between the sun and the Kepler, and you see sort of the ranges there. This is the z-axis, this is the xy axis. So you can actually come up with a pretty good plot of where where to aim your spaceship in order to get from 452b to the sun using these numbers. Okay, in summary, this was an exercise. We're preparing our 60-foot dish at the Deep Space Exploration Society to observe pulsars. And this was an exercise to get the society up to speed on the general nature of pulsars. What are we going to see? What are periods? What are p dots? And how do you actually use this data? We made a lot of assumptions on the ability of an ETI to be able to interpret this map, but I think everything seems reasonable that an advanced civilization would be able to do this, even if they didn't adjust for base 10 or anything like that. They should be able to, if they've got a pulsar database with the pulsar periods, they should be able to interpret the map and come up with the location of the Earth in a probably good enough to find the solar system. Say that once they get to the solar system, that's what that secondary map is, to find the third planet from the sun. So this is an excellent exercise for students in three-dimensional geometry, galactic coordinates, pulsar spin dynamics, and I highly recommend you use this to prepare any of your teammates for pulsars in general. Please go ahead and look at our the two websites, Society of Amateur Radio Astronomers and the Deep Space Exploration Society. Thank you for your time.